Hello and welcome to the KIM-1 Resurrection Series, Episode 6. In this episode, we'll be looking at the RAM in this chip here, and the RAM in the chip hiding under there, and the RAM along here. We'll be testing all of it to see if it's working and see where we need to go from that. To do that, we'll be using this board that we had used in the last episode. I shall be reprogramming the EPROM on there with the code shown on the screen here. This is similar to the code we was running in the ROM check, but this time it's going to be looking at the RAM instead. So we've got, go to the top, start with some NOPs as before, and we come in at F822 as before. Now we preload the X and Y registers with 0, and then we preload the A register with 55. So that will be 0101 0101. And we'll be storing that A register into memory address 0, because it's this address plus what's in the X register. And then we'll be loading back into the Y register from that address plus the X register offset. So that's write 55 out and then read 55 back. We'll then put AA into the A register, which is 10101010. That's the opposite bits to 55. Then we'll store that out to the same memory location, then read it back again. We then increment the X register, and then if the counter has not reached all the way around to 0 again, we shall loop back to here, so the X register will have 1 in it at this point, and we'll write out the same again, or read and write. This is to check that the write cycle and the read cycle of the memory works, and that will be writing out the memory address 1 this time. So that'll be address 0 plus what's in the X register, which will be a 1 bar then, so memory address 1 will get checked. And we'll keep doing that for the first 256 bytes. After that, we'll come to here. And you see the offset has got 256 on it already. So we do the same again. So we're going from 100 to 1FF. Then again here with 200 to 2FF. And then here be 300 to 3FF. That's all the 1K of memory that sits at the bottom. So that's this memory up here. After we've done that, I shall reprogram the EPROM to do this code, which is almost identical, except we're doing a slightly different address. Now we're preloading the X register with 80, and we'll be starting at address 1780. That's the base address of the RAM that's stored in these two ICs sitting here. They both one follow after the other, so we can do both of them in the same loop. So that's 128 bytes. There's 64 bytes in each. So we start with the bottom one, writing the 55 and the AA, looping around again, and this, so we'll have this address plus the X register. The X register will keep counting up, and it'll only count up 128 this time, and that will test all the RAM in those lower two chips. Obviously, we'll be looking at all this with the logic analyzer to see what values we get going backwards and forwards. Okay, so let's remove that EPROM. So here we are with the programmer. Let's pop that in. Oh, no, there's no point in putting that yet. Got to erase it first. So let's get out the magic eraser. And I normally run it off USB because it's a brighter light than if you run it off the batteries. Plug this in and turn it on. We're going to come on this time. Had a bit of trouble last time. Yeah, I'm on. Oh, it's on. It's not very bright. There we go. Right. There's a switch in here that tells whether you're tilted or not, so you have to be up the right way. So we'll just place that on top of there and come back in 5 minutes time. Okay, that's been about 8 or 9 minutes. Let's see whether that worked. Right, so pop it in here. Get out the right way. Go. Nope. It's around that way. There we go. I'll just expect the handle to be at the top. And we'll plug that in. And down here, I think. Right. So run up the software for that. Okay, let's plug the EPROM in and read it. So we've got read it, and we're got a clear EPROM. So now let's program it. So load in the file we want. We do the bottom memory first, and do a program. And that all seems to be there. There's the vectors for the start, right at the end. And there's the program sitting there. So now we'll pop that back into the card. Make sure I get it the right way round. And now we'll have to run it and test it all. Okay, that's all plugged in. Got the power supply up. And blah, blah, blah. Put it on. No, that's not working. Oh, let's plug it in. There we go. And it's running. Okay, we'll have COM3, 4 meg, 32 channels, positive trigger, and right, hold the reset down. Press the arm button and release. There we go. Let's see what data we got with that. Okay, right, let's load that in. There we go. Separating values, test, okay. Store session setup, get rid of that. Alright, now we've got to make sure we're at the beginning. And let's scroll down. Don't want that one. Here's the start. Alright, here's the loading. Let's bring up the actual code. So here we are with the disassembly listing. So we can follow what's going through. So where's the start? Here's the start, 22F8. So it's 22, which is there. So I should get an A2, and then a 0, 0. Yeah, that's correct. Move that along. And we get A0 there, 0, 0. That's correct. Then A9, 55. Correct. And then we've got 9D, 0, 0, 0, 0. So let's go through that bit of the start. So we've got load X with 0, load X with 0, load Y with 0, done that. Then we've got load A with 55, so that's that one. Load A with 55, so the data's coming nicely off the ROM chip. And we've got, right, store A into address 00 plus whatever is in the X register, which in this instance is 0. So D9 store, move it over again, about there. So that's 0, 0 plus the X register, which is 0. So we've got address 0 there, and we're meant to be storing out what's in the A register, which is 55. And we've got, oh no, there it is. That's just random data on the bus while the addition is going on inside the processor. So there's the actual data getting put out into memory. So next one, BC00 is load the Y register from that memory location. BC, there's BC, load Y from 0, 0, plus the calculation, which happens to be a D5 on the bus at that time. And we should get back in a 55, and we're getting an A9. Is that correct? Oh no, that's the next bit. Where are we? Oh, sorry, D5, I've jumped a bit, that is it. It didn't do a calculation on the address. That doesn't matter. So that's the data coming in. There's address 0, reading address 0, and we're getting D5, and it should be a 55 coming back in. Because we had 55 in the A register, we put it into memory, and then we're reading it back again. So what we got here, we should have 1, 0, 1, 0, 1, 0, 1, 0. So the top bit, bit 7, is on, and it shouldn't be. So it looks like the RAM might be bad as well. Okay, so the next one is load AA into the A register. So A9, AA, load A with AA, which is the alternate bits. So we bring that over here, bring it back up. So loaded AA into the A register, and now it's store A into the address 00 plus whatever's in the X, which is 0 again, which is AA. That's the calculated bit again, I think. I'm a little bit worried about that. But anyhow, that's what should be going into that address. So we're definitely putting out the correct value onto the data bus, and that's where it should be going. Then BC is load the Y register from that address. So load from 00 plus the X register back into the Y register. So there's the address 00 gone out again, and the data we got back this time is EA. So we should have a 01, 01, 01, 01. So bit 6 is on as well. So both those bits seem to be on all the time. And go a little bit further up. Got E8 is increment the X register. Then we should do the same again. This time we'll be doing address 1 this time. So we've got branch if not equal back to 26. So here we go. We branch back to 26 there on the address. And we're back up to here, which is load 55 into the A register. Store that into address 0, 00 plus 1, which we had that D5 before. We now got D6 there. That's something to do with it going on internal. But we've got address 1 sitting on the bus. Memory address 1, and we're putting 55 out to it. The next one should be loaded back in. So BC, load address 0, back in, and we're getting D5 coming. We've got, should be 55, not D5. So this top bit is still set, coming in from address 1. So address 1 is faulty as well. So it could be all of them just on those 2 bits. Let's jump much further up and see what we get further up in the addressing range. What addresses we get in? 35. So we are in 35. There we go. And we're getting EA coming in again. There we are. Load 55 in. 55 gets loaded into the A register there. And we're going to store it in location 30. There's 55 going into location 30. And we're going to read it back again. There we go. Read it back again there. And we're getting D5 back there. So further up in the RAM, it's that's the next 256 bytes. It's bad there as well. Looks like those chips are bad all the way. There's the EA again. bits 6 and 7 are on all the time. We will test this with the oscilloscope to see what's going on. So I'll flick back to the other camera. Here we got the book with the ICs in. There's the static RAM chips. So we're looking at these two up here. So that's U5 and U6. Now you may notice that we've got this buffer chip here. That's on the output. The input is connected to the data bus all the time. So we can measure what's going on and off there. And we can actually measure what's going out on this pin, on pin 12. So we can basically isolate the output of that IC from the bus without having to disconnect anything. We can just put the probe straight in there. So let's do that and see whether these actually switch at all, because according to the logic analyzer, these are on all the time and these ones should be switching. So we'll switch over to that and see what we get in there. This is with the red trace is on D7 output and the yellow trace is on D5 output, so they should both be the same. 5 appears to be working, going on and off, but 7's got this weird noise. Let's freeze that. There we go. Here's D5 coming on. So 5 and 7 should be switched on at the same time because we're doing 55s and A80s going through. So that comes on. Well, yeah, it's on here and then switches off for a while. And on for a while. Got these little spikes in between. Providing they're not on the phase 2 switching, that should be okay. We're getting all this noise here. Goodness knows what that is. So the red one is D7, goes low for a little while. How long is that? That's 2 microseconds. 2 microseconds. And comes on again. Then bounces again. It's on most of the time, but it does actually switch off. This is peculiar. Let's connect up to K0 and see what we get. Okay, so the yellow is K0, negative is enabled, so down here is enabled and this is disabled, so the memory is disabled up here. Notice that's 5 volts, we're only getting 3 volts out of the memory, although the spec of the 6502 is only 2.5 volts, so that should be enough to drive it. I'm not sure what the spec of the MM2102 RAM chip is, but that should be enough. It is on the other channels as we saw. So this is D7. As soon as it's selected, we just get a nice big oscillation going on. And then it deselects and it goes high again. Got a longer selection there and a shorter one there. One must be a write and one must be a read, I'll guess. So that'd be the write and that's the read. And it loops around again. Let's do the same again, but for a channel that's working. Okay, this is on D5. Yellow is the chip select. Chip select comes on. And there's the output from D5. It's positive. And there's a select again. 0, 0, 1. Bear in mind this is just the output, so we don't know what's going in. This is just what the output's doing. So here I think this is a read. We're reading on 1 here. And we're reading a 0 there. Yeah, because it's the output. So you've got your initial bit of a spike. If it's already low, if it was low before it stays low. If it was high before it stays high. That's just, I think it's just drifting off because it's open circuited. So the voltage is gradually draining off. Boom, I'm on 1 here. I'm on 0 here. 0 here. I'm on 1 here. So that's what it should look like. Okay, I've connected this onto the D6 signal. So you can see the chip selects going on and off, and we've just got this nasty little wiggle between 1 and 2 volts on the data out on D6. I'll go through and check all the others just to see what we're getting off those, but I suspect they'll all be okay. There's something interesting here. This is the chip select again. The yellow and the red is data in on D7, switching between 4 volts and 0 volts. But when the chip is selected, we get all these lovely oscillations. That's on the data in, not the data out. So in and out are oscillating when it's selected. although the oscillation seems to die down here and not so much there because it's the amount of time it's taking. So is the input bouncing up and down and it's actually storing it correctly? It's puzzling. I have to poke around and think about this. Here we've got the read-write signal in yellow. So low is write, high is read. And the red trace is D7. Now here we're doing a write. I think that might be trying to write a 1 because there's a little blip there. But the actual data gets written in when the that strobe goes high. This read-write is the RAM read-write and it's all keyed in with the phase 2 clock. Now this, I'll guess, is a read. We just get lots of noise come out. And then we do another write here, which is, I'll guess, writing a 0 because it's at the base. If we scroll that along, you'll see we get another little blip in that one, then nothing in that one. It just keeps repeating again and again. So as if it's trying to write a 1, 0, 1, 0. Whenever we do a read, or whenever the read pulse is, it's picking it up as a positive. This oscillation here could be caused by another IC. If we flick cameras to this one, this is the diagram again. On this IC here, right into the middle, there's 2 of these and they buffer all the outputs. So the top 4 RAM chips here through this buffer and the bottom 4 RAM chips through another buffer. If this circuit is oscillating, when it gets enabled, the output of this feeds around. So if this is oscillating, this will be going on, off, on, off, on, off, and it could be saving at just the wrong time, so it always actually has a 1 saved in there. So when you try and put it out, it puts a 1 out. Well, it tries to, but this is going to be oscillating like crazy. This one, on the other hand, is just low, so it could be, this is in the same IC, so it could be this IC that's damaged, and this is putting 1 volt out here, or 1.5 volts, 1 to 2 volts sitting on here all the time, thus screwing everything up when this is enabled. It won't be the actual enabling circuit here because the other bits work, so we know that bit's okay. And the this bit over here is the read-write, the RAM read-write. There's a delay in it created by, you can see it, this circuit here, but your phase 2 clock comes in here. So when you're doing a write and the phase 2 goes high, you get your RAM write signal comes out. When it's a read, it's on all the time. And this is your normal read-write if you go to a ROM, etc. I'm not quite sure why that's delayed, but it is. That should be okay. There's the actual timing diagram. We've got this is your normal read-write signal, but the RAM read-write doesn't come down until we've actually got a phase 2 clock. So you'd have like a line down here and up there, and this is the point where it actually reads the data in. And if the oscillations do seem to be quite consistent, so if it's consistently reading in, that's going high as the oscillations are high, then we'll get a 1 out all the time. As far as D6 is concerned, well, obviously the CPU sees that 1 to 2 volts as a 1, so that's on all the time. So I'm inclined to change this IC here because it's quite a common one and easier to get hold of. These ICs might be okay. So before I order any of those, I'll look up this one and see how I can prove or disprove any of that. Here's a close-up of the oscillations on the output. So the red is the output pin of the memory chip, and the yellow is the output from the buffer chip going out. The output from the buffer seems to be quite neat and tidy, but actually memory output is bouncing a bit, and you've got this little blip on each oscillation. It's oscillating about 3 megahertz, but this little blip here might be to do with the transistor switching. And you get this little blip later on, and this bit here, if you go through the scans, only happens about 1 in 4 cycles. If I can move this along, let's start reading. If I move this along, go back, that's just the data bus going on and off. So there's another one there where it's oscillating, but there's no blip afterwards. And another one without the blip. And most of the data out was being held high on those two. Next one, same again. And if we're going all the way back, here we go, we've got the same sort of thing again. I can see a bit of a pattern there. These do a blip when the data's low. So the yellow one is the actually connected to the data bus that runs around everything else. At this point, if it's low at that point, as if we get a couple more oscillations, but are held to about 1 volt. This is peculiar. I'm not sure what's causing it. I'm tending towards the memory chip again here. I'll see what the actual logic chip is. Might pull that one out just to start with, just to isolate some ins and outs. We go back to the actual manual. I'll bring it a bit closer so you can see. Just to make things more confusing, these buffer chips. Oh, let's get on the right. No, you won't be able to see it. Hold on. Here's me. I'll use my finger. These buffer chips here are wrong. These ones, this is U13 and this is U14. And because of that, all the pin numbers are wrong. I've actually just traced it all out on the track, build it out. So this is definitely D7. And they've got this labelled up wrong, which makes life a bit more difficult when trying to fault find. This is the IC in question. So that's D7, and it definitely feeds around to here, which is U13. And it's coming round to these 3 pins over here. The top one's the enable in pin 1, and then pin 2 and pin 3 are connected over here on U5, which is D7. Well, I've ordered the chips. In the meantime, I think I'll change the software to test the memory in these two ICs, that one and the one hiding under there, to see how whether they're working. I suspect that this one is still going to chuck up the same errors as the rest of it. So here's the results for testing the RIOT chip RAMs that start at 1780 up to 17FF. Had a bit of trouble with this. I like to reprogram the ROM chip again, but let's see what we got. We start from the beginning. We got, there we go, there's the start vector, F822. And here's the program. So go through the program. We're going to load the X register with 80 this time. The Y register we're just going to clear. Then we're going to load the A register with 55. And then we're going to store the A register in address 1700 plus whatever's in the X register. So that'll be 1700. And then we're going to load the Y register with what was stored there. So we're going to read it back basically. And then we're going to load the A register with AA this time. And then save it to the same address and read it back again. Then we increment the X register and loop round again and do the 55 AA again, but this time we'll go in 1701 because X will have a 1 in it, and so forth and such, counting up all the way to 17FF, at which point the loop will drop down to here and it'll come back round here and load it back in with 80 again, and we just keep cycling around. So if we look at the values we've actually got, so there's A280 there, which is load the X register. Then A00, load the Y register with 0. And then A9 is load the A register with 55. So now we've got 9D, which is store the A register into address 1700 plus the X register. So that's 1780, because the X register's got 80 in it. And there's a value 55 going out there to be strobed into that memory address. We go further along, and we go into BC017 plus the 80, which is read it back in. So we've got 1780 on the address, and we read back 55. So that was successful. So the first, well, the right chip number 003, the RAM, the first byte, seems to be working at the moment, but we'll carry on. And we've got load AA into the A register, and then we're going to save it out to the same address. So that's there. Ignore that 55, that's old data. That's where the bus has changed to AA. We're writing AA out to this memory address. Then we're going to read it back in again. Read the same address back in, and we've got AA. So all the bits seem to be turning on and off in the first byte at any rate. If we move further along, just look at the addresses at the bottom, we'll be able to pick out where we're reading and writing. So there we go, 55 written out to address 1781. And we read it back there. And then we're going to write out an AA there to that address. There's the AA written out to that address. And coming back, we've got an AA coming back. So the bottom one seems to be working. Now what we need to do is find address 17CO. Oops, wrong button. 17CO. Have we got enough samples? Let's see what we got just here, shall we? Oops. Where are we? 1797. No, not there yet. Oh, keep pressing that button, just take my hand away. And what we got here? 17AO. Not there yet. Keep going. And 17C4. Here we go. So let's find the first one. 17C3, C2, C1. 17CO. That's the first address in the O2 RIOT chip, the one we've got ROM problems with. Okay, so load the A register with 55 and write it out to that address with C0 in the X register. So we put in a 55 out onto the bus, save it, and if we read back that address, we've got a 16. We had zeros before, didn't we? We had, it was bit 1 and 0 and 1 had the, we'll get this right in a minute. D0 and D6 had the problems. So D0's got 0 in, D1's got 0 in, stuck on. So what we've got on this one's going to do an AA, write that out, and then we'll read it back. There's the AA being written out, and reading it back. Oh, we've got an AA coming because bit 0 and bit 6 are both off on that test anyhow. So it's passing that test but failing the other. So it's not just the ROM on the right chip that's failed, it's the actual digital pins that have failed. We definitely need to sort out that RIOT chip. Oh dear, oh dear. So 2 or 3 chips dead at least. So I hope you enjoyed that. Make lots of comments below. And I've ordered some more chips, so when they've come in, I'll make another video. So don't forget to like and subscribe, and I'll hopefully see you when I've got the new chips to fit in place.